Welcome everyone back to section 5.2 volumes. In this video we're going to expand what we did in the first video and calculate volumes of more difficult solids of revolution, and then we're going to move on to calculate volumes of things that aren't even solids of revolution. Let's get to it. Okay, here in 5.2.7 this is now different. So we don't have our favorite region anymore. We have y equals the square root of x equals 0, y equals 2, x equals 1, and we're rotating it about the line y equals 3, so it's all different. So I want to draw a picture and, of course, calculate the volume that we're finding here. So the first thing I'm going to draw is this nice square root of x. X equals 0 is, of course, the y-axis. I have y equals 2, which is the top part, and x equals 1, which is the side to the right. So this right here is my region R. And now I want to rotate this about the line y equals 3. So I can tell already that I didn't give myself enough room here. I need to try to scoot all of this down a little bit. So I'm going to use the magic of technology and scoot it all down. And we're going to rotate this, like I said, about this line y equals 3. So if I take this nice horizontal line and I was to rotate this around y equals 3, well, this would be distance 1 away still, so it would look like this line up here. And then if I took this nice blue line and I rotated it around y equals 3, you can see it's, well, distance 2 up here, so that'd be distance 2 away at 5. And it's distance 3 away down here, so that's going to be distance 3 away up here, 6. And so that's what the blue line would look like if I rotated it up just 180 degrees. So that's kind of, some mirror image about this line, y equals 3. So I'm going to be rotating it around y equals 3. So in general, it's going to look like a tree stump, almost. A tree stump that's been hollowed out in the middle. And we have lots of washers, it looks like. So we're going to be using the washer method. Okay, let me just highlight some of these so we can get the areas. So these are the areas that we're going to be adding up. And when we add up all of these areas, that's going to give us our volume. Okay, so we're slicing this, as we can see, with respect to x. We have x slices going up and down. So I'm going to want to integrate this with respect to x. So let's go ahead and write down an integral with respect to x. And let's see, we have pi times the outer radius squared minus pi times the inner radius squared. So we need to figure out what are those outer and inner radii. All right, so looking at this a little bit closer, and first of all, let's tackle the inner radius. The inner radius seems to be staying constant. Right, that's my red line right here. And in some sense, that's because the top of the region is this y equals 2, and the line that we're rotating about is y equals 3. So the inner radius is going to be 1. Nice and easy. Now the outer radius, on the other hand, is changing. So if I'm going to use my blue pen now to try to sketch just a couple instances of the outer radius. Here are my outer radius in my blue pen. And we can see that these are some heights that are changing, right? The smaller one seems to be right around 2. The bigger one seems to be right around 3. So they should be numbers between 2 and 3. And they have something to do with this lower curve, y equals the square root of x. And of course, the line that we're rotating it about is where they stop. That's going to be y equals 3. So now look at these. I'm going to draw this nice brown line for 3. And these heights, which correspond to y equals the square root of x, kind of underneath there. And we can see if we took 3 and we subtracted away that height, the square root of x, then that would give us what we want. That would give us those blue lines there. It's the difference between 3, this long height, minus the square root of x, which is the height under this curve. All right, let me just bold these really quick. Okay, so the outer radius, pi times 3 minus root x, and I have to square all of that. And we're integrating again with respect to x. Let's remind ourselves what should be the lower and the upper limit, right? So the lowest x value is 0 and the biggest x value is 1. So again, we're integrating from 0 to 1 here. Okay, so maybe a good next step, I don't think I can just integrate this. I should maybe expand it out a little bit. So if I expand this out, the claim is that I get 9 minus 2 times root x plus x. And then, of course, 1 squared is just 1. And the big thing is that you have to remember to FOIL this, right? If you FOIL it, you get this negative 2 root x term. If you just distribute it as 3 squared and negative square root of x squared, you don't get the right answer. That is bad. Okay, so let's expand this out one more time. So we get 9 pi minus 2 pi root x plus pi x minus pi dx. Now notice we can actually simplify this a little bit more. So I'm going to try to do two things in one. I'm going to try to integrate and simplify that down. So that's going to be 8 pi, and when I integrate with respect to x, I get an extra x. Now when I integrate the root x, we get 2/3 x to the 3/2. And now when I integrate pi x, I get pi over 2 x squared. And again, we're integrating that from 0 to 1. And I'm going to plug in those 1s and 0s kind of term by term. So for instance, here I get 8 pi times 1 minus 0. And now I can express this as negative 4 pi over 3 times, now if I plug in 1 for x to the 3/2 and 0 to x to the 3/2, the claim is that I get is 1 and 0. And same thing when I plug this in for x squared. So this becomes 8 pi minus 4 pi over 3 plus pi over 2, which if you have a lot of time, you can simplify this down. You need sixths, which means you're going to get something like 48 pi over 6 minus 8 pi over 6 plus 3 pi over 6. And now that we have a common denominator, this is going to give us 43 pi over 6, which is our final answer. That is the volume of our tree stump with a hole drilled out of it. Let's try one more solid of revolution. So region in the xy plane, bounded by y equals 0, x equals 0, and y equals 1 minus x. Find the volume of the solid generated by revolving this about the line x equals 2. So I want us to get some practice revolving about other lines rather than just the x and the y axis. So in the previous one we did y equals 3. Now we're doing x equals 2 to give us some experience with that. So first let's draw this region. So y equals 0 and x equals 0. Well, that's the x and the y axis. And then the line y equals 1 minus x. Well, this is this nice line. It has slope -1 and y-intercept +1. So here's my region. And I'm going to be revolving this around the line x equals 2. So this is a nice vertical line where x equals 2. And I almost gave myself enough room this time. So if I spin this around, this line x equals 2, we can see I'm going to get washers again. And here's this top point up here if I was to revolve that around the line y equals 2. And some points in the middle. Let's try that one again. So washers. At the top they seem very, very thin, and down at the bottom they seem a little bit thicker. And like I did in my last problem, we could draw kind of what that region looks like if I had reflected it about this x equals 2. So it's going to again be some triangle thing. And so I'm going to want to use my washer method. So my washer method says that I need to integrate pi times the outer radius squared minus pi times the inner radius squared. And the big thing here is that I'm integrating with respect to y. You can see that these washers are broken up, in y slices that are perpendicular to the y-axis. And so again, I need to try to figure out what are those inner and outer radiuses. So let's try to take a look a little bit closer to figure that out. In this case, the easy one is going to be the outer radius. We can see even as my y changes, as it gets bigger and bigger, my outer radius stays the same, and that outer radius is 2. My inner radius, on the other hand, this one's changing. At the bottom, it's pretty small, and then it gets bigger and bigger until it's finally 2. And let me draw in, I'm going to re-emphasize these purples here, and I'll draw the outer radius really quick, pi 2 squared minus, okay, now I need to do a little bit more work for the inner radius. And let me use blue here really quick to denote, I do know one length, right? I know that this width right here is somehow related to this line y equals 1 minus x. Since I want the width, I want the x value though. So I could solve this for x. And if I solved it for x, I would get x is equal to 1 minus y. So let me I'll add x to the other side. I'll subtract y from both sides. So yeah, that width, that blue line is 1 minus y. And so remember, I'm trying to figure out what that red line is. Well, we know that purple line is 2 though, right? So the purple line is 2, and that blue line is 1 minus y. So if I want the red line, I should take that full purple line 2, and I should subtract away this blue line, this 1 minus y. So if I do that, I'll write it down really quick, 2 minus 1 minus y. That should give me the red line. So if I simplify that, I'll do that here in a second. Let me just write down 2 minus 1 minus y. And remember, I'm squaring all that. Oops, and I forgot my pi. There we go. Now we can simplify this down in my next line. So first of all, if I square 2, that's going to give me 4. Oops, 1 second. And now if I simplify this whole thing that I need to square, that's going to be 2 minus 1 is 1, and negative y is positive y. And now I have to be careful again when I FOIL. So 1 plus 2y plus y squared. Now we're basically safe in Calc 1 world. We just need to spend a little time simplifying this all down and then integrating carefully. But the hard thing is really setting these up. So I distributed my negative pi. Again, you have to be careful to distribute that negative. And now I'm going to go ahead and integrate, and I'm going to try to combine that 4 pi and the negative pi. Again, I'm integrating from 0 to 1. And if I plug in 0 and 1 for my first term, for my second term, and for my third term, you'll notice that when you square 0 and when you square 1, or when you cube 0 and when you cube 1, they stay 0 and 1. So this simplifies down nicely to 2 pi minus pi over 3, or another way we can express this as 5 pi over 3. All right, and there is my final answer. That is the volume of this solid of revolution. Okay, now we want to move on to a new topic, and that new topic is, what about volumes that aren't solids of revolutions? So in this case, we have a solid from a triangular base formed from y equals x over 2, y equals 0, and x equals 4, and we have parallel cross sections perpendicular to the base and the x-axis, which are squares. And I want to find the volume of such a solid. So we see I have a nice picture given to you. It kind of makes a nice solid here. It looks like some sort of cone almost. So here is my xy plane. And this line right here is going to be that y equals x over 2 that they talk about above. Here is y equals 0. And then finally I have x equals 4. So that's all in the xy plane. It's a little bit weird because it's tilted on its side. And then we can see that we have these cross sections, which are squares. Well, they're all parallel to one another, and they're perpendicular to that base. So when I'm adding up areas, my areas are going to be of squares, right? So volume I know is, I should integrate area. And it makes sense to integrate with respect to x since these are all chopped up, and we have these small x's between all these squares. And so my smallest x value is 0 and my largest x value is 4. So here we are. Again, my area is of a square, so that's going to be its length, whatever that is, squared. And so the big thing is that I need to figure out what is this distance here, right? Because that's my L. And of course, it depends on x. And so that's the difference between these two lines right here. It's the vertical distance or the y distance. So that's going to be x over 2 minus x equals 0, so 0. So I take that length and I square it. And now I'm set up. Again, this is the hard part. This is the new thing that we're doing here in Calc 2. Now integrating this is a nice, easy Calc 1 topic. So I can square both the numerator and the denominator. I can integrate this, and I can plug in 0 and 4, which is a little bit difficult, right? Because I have 4 cubed, which is 64. And I can simplify that a little bit down to 16 thirds. Okay, so we see now that we can find volumes of things more than just solids of revolution, right? So let's try one more here, the last one for the section, and that is to find the volume of some solid whose base is B, and this is the region bounded by y equals x squared and y equals 1. So this is going to be this parabola looking thing. And cross sections are perpendicular to the y-axis, are equilateral triangles. So again, thank goodness they gave me a picture here. Let me sketch out my base region B, y equals x squared and y equals 1. This is what I'm going to be integrating over. And certainly we can see these nice equilateral triangles are my cross section. So I'm going to want to figure out what is the area of these things, right? I'm going to be adding up the areas of equilateral triangles. Let me just shade these in orange, as I've done before. And so this is going to take a little bit of work. Let me just write down really quick our definition. Again, since we see that these are perpendicular to the y-axis, it makes sense that we're going to integrate with respect to y. And it looks like the lowest y value is 0, the biggest y value is 1, so my limits are going to be 0 to 1. Write those things down to at least get some partial credit going. And I need to figure out this L, right? I need to figure out what this length is for my base of an equilateral triangle, and hopefully if I can figure out what those L's are, then I can figure out the area of this thing. And the idea here is that I'm going to break this down into 2 right triangles. And remember that the area of a triangle is 1/2 base times height. And so the base of this thing is L. But the height, I don't know. The height is right here. So in order to figure out what that is, I'm going to need to use the Pythagorean theorem. So here's my nice right triangle, and I need to solve for h. So that is, the Pythagorean theorem says if I square both of the legs, add those together, that'll be the hypotenuse squared. So I can solve this for h squared as 3l squared over 4, and then finally I can take the square root. And because I know, let me move this up a little bit. And because this is a positive height, I know that it's going to be the positive root, right? Because technically when you take the square root, you should have a plus and a minus. So this is going to be the square root of 3, L over 2. I can simplify that down to the square root of 3 over 4 L squared. That is my area formula. Okay, so now I have area with regard to L, but I need it with regard to Y, right? I need to integrate stuff with Y. So I need to figure out how is L and Y related. And well, we can see here are some nice widths here, and they have to do with what is the distance to this x squared. So let me draw this. This is a little bit confusing in the xy plane, right? So those red lines that I drew are these here. Okay, so if I want to figure out what are those widths, well, this has something to do with y equals x squared, but it's the width of it. So I should solve for x, right? It's some x value. So if I solve this for x, well, I'm going to have the square root of y. And this is almost the same thing as the length, but the only problem is that my length goes from one side of the parabola to the other. So the claim is that length is 2 times the square root of y. Let's take a look here. Right, here's all my lengths. They go to both sides. If I draw those down here, yes. So hopefully everyone sees that my length is 2 times the square root of y. So now if I replace that in my area formula, the claim is that I'm just about done. I almost have the setup. So this is going to be the square root of 3 over 4, and instead of L squared, I'm going to put 2 square root of y and square that. Integrate that with respect to y, right, because of dy's, that's a good sign, from 0 to 1. Okay, so now let's see, if I square this thing, I'm going to get 4y. That's nice. Those 4's are going to cancel a little bit. And now the square root of 3 is along for the ride, but when I integrate y, I get y squared over 2 from 0 to 1. And let's see, plugging in 0 does nothing. Plugging in 1 gives me the square root of 3 over 2. And that will be my final answer. All right, so that is the end of 5.2. Good job hanging in there. I know this was a long video. Go ahead and get started on your web work, and I'll see you next time. 5.4 work. See you then.